Also, I just want to say just thank you guys for taking time out of your day to share your projects with us. It's cool for students to see all the different things that you guys do on campus and for the school.
Okay, let me get my slides up someplace, and then I will start. Um, okay, sure, you should now see the title and a bit
Yes.
of an abstract. Why we need asynchronous communications in parallel computing and some thoughts on how to do it. Uh, this, by the way, I remember a few years ago, I read a book entitled Partly Baked uh, Inventions, Theories, whatever. You know how you have half-baked things that are not fully working or not fully, well, Partly Baked says maybe this theory is almost done, but not quite. It's like 80% baked, or this is very preliminary. It's maybe still raw dough. What I'm about to present is partly baked. I'm going to give you some background, which I've been working on for a couple of years, but the actual key idea of this that results in this talk is something I came up with Monday of this week, and I've been somewhat developing it since. So let me explain what's going on. We're going to start with talking about an SPMD parallel execution. What does that mean? Well, basically, it's the standard easy thing that everybody does. You've got, for instance, one program that's designed to run in parallel. You write this thing in C or C++ and use MPI communications, that being the message passing interface, which is a standard developed in the 90s and which pretty much everybody uses when you're running something on a cluster of computers. In particular, SPND execution runs as multiple different processes, which may be on the same computer or on multiple machines on a cluster. Each computer is running the same code, but they're all, rather, each process is the same code, but they all have presumably different data. That's where the parallelism comes in. So you've got, for example, 20 processes numbered 0 to 19, and they all have identical code, but they all have different data. So they might actually be doing different tasks at the same time. For example, you may have an if statement somewhere in the code, and depending on the data, some processes do the if condition and other processes may do the else condition. You do have the same local variables, which makes it fairly straightforward to send stuff from one process to another. You can send X to process 5, for instance, from process 1, and process 5 knows what X is because it's the same code. There's a variable called X of the same type. Okay. Now, we want to talk about processes. So I want to talk a little bit about the code, and we'll be coming back to that. Here is an example, a sample code in, essentially this was done in Fortran, by the way, and you may be surprised to know that Fortran is making a comeback. There is a renewed interest in Fortran as of last month. So don't assume it's a dead language just because it was invented in 1960. It's still around and still being used. Okay, now, so we've got some code in Fortran here. And what I want to, a useful representation of the code is what's called a control flow graph. This here is a control flow graph. Now, how do you get that? Well, you analyze the code and you identify basic blocks in the code. What's a basic block? It's a set of lines in the code that always get executed together. So essentially, you've got a chunk of code and it is delimited by control statements. So you have, for example, block 1, which is what you do at the start. I have actually divided the code up in this by communications. I'm assuming there's a communications here, for instance. So, but really, this stuff always gets done together. And then at the end of this chunk, you have a choice. You go to this code or this code or that code. And this is done through a a very entertaining Fortran statement. If X1 go to 10, 20, or 30, and this is essentially a switch statement, but it's a switch statement on X1 that says if X1 is negative, go to 10. If X1 is 0, go to 20. And if X1 is positive, go to 30. So it's a very primitive switch statement. So, and then what these circles are, well, this is the code you get to if you take option 1 or the first option. This is the code you get to on the second option. This is the code you get to on the third option. And you keep on like this. Since the code is defined, the blocks are defined by control logic, mostly what this shows is what are the alternatives and what are the possible paths through the code. So we see that in one case, it just goes into here and then it can loop. These arcs going backwards are loops. Then it can loop among these 3 blocks several times. Then from here, then it can exit. It actually has 2 exits from this loop. It can go directly to block 17, or it can exit from block 15 to 16. Imagine, for instance, a while loop with a break statement in it. So one of these things is the normal exit, probably this one, and another one is an extra different exit on some special condition. And then you do these blocks and reach an end block. Here on this alternative, there's an if-else condition here, and then you go into another loop that actually has a loop nested inside it. And anyway, the neat thing about this representation is that the logic is presumably the same no matter what you're doing. You translate this code to assembly language, and the logic will be the same even though the statements gets translated. So this is kind of a machine independent view of what the code is doing and what it's looked like. And you can just say, for instance, block 4, what does block 4 do? Well, in this case, it doesn't do anything. It's a Fortran continue statement. But you can imagine by looking at that block, for instance, let's look at a block that actually does something. For instance, blocks 8 and 9 here. What do? Well, they do statement set E. So that's what's being repeated by this little loop between 8 and 9. So you can, but the statement set itself can be in anything you want. It can be in a high level language like C++. It can be in an even higher level language like Scheme. It can be in low level assembly. It can even be machine language. But we've got these chunks of code that always get executed together. Why do they get executed together? Because there's no control logic in it. So we're going to use this to define an execution, because now we can say, okay, what are the possible executions for this program? Well, everybody starts in block 1. Then, for example, 1, 2, 4, 5, 8, 9, 8, 9, 8, 9, 8, 9, 10, 11, 12, 20. I've just given you a list of blocks, but those blocks correspond to a possible path through the code. Any execution can be described by some path in this diagram as essentially a list of these blocks that get executed, sometimes uniquely, sometimes repeatedly if you've got into a loop, but it gives you a very compact description of what an execution looks like. And you can imagine every one of these blocks to be essentially a black box You can define what's going on in block 2 by saying what it does to memory. Similarly, what goes on in block 4, that's what it does to memory, and so on down the line. So and you get that same thing in everywhere else in this diagram. So we're going to use basic blocks to describe executions, and we can use them to describe the state of a process at any given time. We can say a process state can be defined by what block is being executed, because the block tells you what the code's doing. And you also need the memory content, right? The combination of what's in memory and what code is being executed is a complete description of the state of the program. And you could use it, for instance, you could halt the program, and then you could just say, okay, we restore the state of memory, we execute this block, the program goes on from wherever it was. A transition, which we can call a step, happens when you finish one basic block and move to another basic block. The neat thing about basic blocks is it keeps us from having to worry about, well, is a step a single line of code? Is a step a machine level instruction? Is a step, you get all kinds of inconsistent definitions. That once you get into basic blocks, you now can say, okay, of course it's a broader definition. You really want to have the memory at the start of the block, so that you can say, okay, I can restart this whole thing by setting the memory to what it was at the start of the block and going to the start of the block. But that's it. The execution then is a list of states from the start block to the end block, indexed by step. And a parallel state then is easy. For our particular case where we're running multiple copies of this thing, what we can do if we want to know what is the state in parallel is just see, okay, we got 10 processes, for example. What is the memory of process 0 in, and what block is it in? And that tells us the state of process 0. We can do the same thing for process 1, for process 2, and so on the line. So what's the parallel state? Well, it's an ordered list of the individual process states. And we know what they all mean because it's the same code. We've got the block number tells us what each process is doing, and the state of memory, the collective state of memory at every process, tells us all the memory that the program has access to. So there you go. Now we run into a thing, because a sequential transition is a deterministic thing, right? You finish block 10, for example, here, and then depending on what's in memory, you either stay in the loop by jumping back to block 5, or you leave the loop by going forward to block 11. That's a purely deterministic transition, and you know what block 11 can do because you've got the memory, the changes that block 10 did to memory. So that's the starting memory for block 11. And so unless you've got some explicitly random factor thrown in here someplace, this is completely deterministic, and you can tell. And if you run the same parallel process, with the same sequential process, you run it with the same data, you're going to execute the same set of steps, because the choices depend on memory, and the memory depends on what the previous block did, which is, again, assuming no random code, the previous block just depends on the data. So you've got a fully deterministic execution of a single process. But this is not true for a parallel process because of something like this. Parallel determination executions are inherently non-deterministic for this reason. Imagine, for instance, that we've got an execution of 3 processes. They all start at block 0. The starting block is always the same. They all start in block 0, but then when do you get a parallel transition? You get it when the parallel state changes. Suppose, but now which of these 3 processes is going to change state first? That's random. These are, we're going to assume that we've got a separate CPU for each process. So this is running, for instance, this could be a multi-core system, and this is running on one core, this is running on another core, this is running on another core, and they all have a common clock, but which one of them executes first? That may depend on the order of loading, it may depend on which core was hotter, it may depend on what processes the operating system decided to swap in or out, what memory is in cache, et cetera, et cetera. It's complicated. It's going to look kind of random. So we might get, for instance, this process transitions to step 1, and that is a change in a parallel state. But we might also get this process transitions to state 1, and that gives us a different parallel state. This is a state described by the combination 1, 0, 0, whereas this state is described by 0, 1, 0. And the same thing happens for all subsequent states. We might now get, say, both of these processes transition simultaneously. They're running on different cores, of course, so why not? So that gives us a state 2, 1, 1. Here, on the other hand, you just had this one process transitioning, which gives us 1, 1, 0, and this last process is hung up on something for 3 cycles. It doesn't make any kind of transition, so we get the state. The thing is, the set of states that we get in a parallel state is non-deterministic because it depends on all kinds of execution details of who transfers when. Now, you may think this is all pure theory. It's not. It's measurable. We can instrument processes, and I have done this, with code that keeps track of when transitions happen and can reconstruct the parallel state by comparing the traces and see, okay, at some specific time, where was everybody? 10 microseconds later, where was everybody? And so on down the line. So we can generate things that look exactly like this. Traces of what the parallel execution looks like and verify, no, it's not deterministic. Now, this becomes problematic when we want to use the properties of parallel execution by solving a problem that's bigger than what any one process has, right? The advantage of parallel execution in particular is, hey, we got these, say, 10 processes or 15 or 48 processes, and they each have local chunks of memory, but the total memory available to the parallel process is those 48 chunks of memory, which can contain different data, and you can be doing different things concurrently to different chunks of memory. But ideally, the set of parallel tasks is acting on that large memory. It might be shared, it might not be. The details don't particularly matter, but the point is, what is the state of that memory? And here's another thing. You might think, okay, if you got a state shared memory, it avoids the issue. Not so. Each process is working on local memory because each process has a local cache. So it doesn't really matter whether the memory is shared or not. In reality, each process is working on its local memory space. And in order to do parallel computation, at some point or another, we're going to need to transfer from one process's local memory to another process's local memory. And the problem is, how can we do this when we don't know even where that other process is in the computation? Look at this. If we transfer something from process 0, or let's say from process 0 here, and we transfer something to process 0, this time around, process 0 is going to be in state 2. But if we do it from here, for instance, backtrack a little. Consider a transfer from memory at this process, the middle process, to the 0th process, the lowest numbered process. If we do the transfer here, we're processing from state 1 in process 0 to state 1 in the other process. But if we do it here, we're transferring from state 1 to process 2. Similarly to state 2. Similarly, if we go from here to here, these two processes, if this happens to be the parallel state, we're going to be transferring from 1 to 1. But if this is the parallel state, we're going to be transferring from 1 to 0. If we read memory here, we're going to read from here, we're going to read it at state 0, we're going to read here at state 1, we're going to read here at state 2. And the thing is, changes in state like this, when we shift blocks, we can presume that executing blocks changes memory. So we expect the memory at state 2 to be different from the memory at state 1, to be different from the memory at state 0. So which particular blocks are exchanging data matters in terms of what we calculate. If we just let things randomly drift whichever way they want, then we are going to have to do something to make sure that when we're reading the data, we're reading the right version of the data. Hence, synchronization. So before we get to that, let's visualize. Let's see if we can get a visual of what it is that we're doing. Parallel state is, as we saw up here, an ordered n tuple, or an ordered, for instance, this is an ordered set of 3 processes. So how can we represent that? Suppose we got 17 processes, and we have got, each process has a state. Well, the state, let's number the basic blocks from, say, 0 to 20, assuming the program has 20 distinct basic blocks. Then we can say the state of any individual process can be represented on a line that's numbered from 0 to 20, and we can just say, okay, process 5 is at position 6 on that line if it's doing block 6. Now, if you have 2 processes, you can say, okay, we can do this on a plane, right? We have process 0 on the x-axis, process 1 on the y-axis, and then we can identify a point on the plane, and that just tells us what is the state of process 0 and what is the state of process 1. They're the coordinates of that point. We got 17 processes. Then we can imagine we've got a 17-dimensional hypercube. Okay, most of us cannot visualize a 17-dimensional hypercube, but we can compress it. We can project it onto 3 dimensions, and that's what we got here. This is a representation of an execution of an optimization process, 20 iterations of it in particular, actually 200 because we repeat the code, and we find this. Each of these dots on the thing represents, actually it's kind of a projection of a point in 17 dimensions, but you get kind of the feel for it. Time, the 0 point would be, or the origin would be down at the base of this cube. So you can imagine any single process would look like, or if processes were perfectly coordinated with each other, it would look like just a vertical line because the blocks would always match. Processes are not perfectly coordinated, and that's why we get the spread. Some processes advance more in one direction than in others, and when we repeat the loop, the execution doesn't repeat. So we get this cloud of points. You can imagine the central tendency of the whole thing is to go from the bottom to the top. So this thing here represents the end of the loop. This represents the start of the loop. And this stuff around here represents each process is going its own way through the loop doing different things. And so we get this mess. Now, let us synchronize. What is synchronize? Synchronizing is we're going to force processes into particular states. How do we do it? Well, for example, we put a barrier at block 15. And what that means is a process reaches block 15 and then it verifies. Has everybody else reached block 15? If they haven't, it just waits. When everybody reaches block 15, then the barrier is released and everybody can progress. This would cause some kind of a clumping of states around block 15 because processes that get in there are going to just kind of stay there until the barrier gets released. In fact, you get something like this. This particular process is doing two things at the tail end of the loop, at the end of the loop, which would be close to the top of the graph. And we see them here on the graph. This particular clump, the denser one, is probably a reduction operation, which is, all of these things have the semantics of a barrier, but a reduction operation is a stronger synchronization because it requires to gather all the data from every process in usually in one process, but the computations are done spread out. And then once you've got a particular value, then you broadcast that value for everybody else. So it's not an exact barrier. You don't really have to wait until everybody is in one block, but you can kind of think of it as two trees connected at the root. So everybody kind of keeps waiting until at least somebody has data from everybody, and then that data gets spread out on a tree. So it's not exactly a barrier, but it's close. So it looks something like this. We can define synchronizations. Well, why do we use synchronizations? We use it to enforce causality. Because here's the trick. Without synchronization, we can think of something like a process I that calculates something that process J needs. We can look at that as the computation of I causes J to do something. But that depends on having the right value of I, right? That's where the synchronization comes in, because if we don't enforce the order, whatever happens at I happens before J, if you don't enforce that, then you don't know what J is going to do. J could do some random thing because it doesn't have the right value, the newest value of J. J could even do some random thing because it got the value too late. It could do any number of things unless we enforce the order, and that's what synchronization does. But the real key to the whole thing is it enforces causality. I'm going to give you an example. This thing that we've been talking, that I talked about, this 17-dimensional cube, we call that a phase space. And it allows us to describe what the synchronization, what the state of the system is at any given time. And we see that because a point in that space tells you, by just looking at the coordinates of it, it tells you what every process is doing. So it says, okay, this process is in state 5, this other process is in state 7, this one is, you got the picture. Of course, it's not a complete representation, but it is a complete representation of the execution. A full representation would include the memory, but that's a different kettle of fish. We're interested in the execution because what we need for synchronization is just to match up the blocks. For example, if we're doing a barrier operation of some kind, we've got one block that says barrier, and in order for the barrier to release, every process has to reach that block and confirm that it's there. Okay, this is an example with two processes. This is kind of my IJ example of 30 seconds ago. We're having a synchronization here where in which process X is sending something to process Y, but it is a buffered send. You can imagine that what we're really graphing here is the difference between the block number at which the synchronization occurs and block numbers before and block numbers after. So essentially, process X is moving this way, is advancing this way, it hits the synchronization, it does its thing, it continues. We're using a buffered send, so it doesn't have to wait. It just says, okay, I get here, I'm gonna put the data I want process Y to have in this buffer, and I can keep going. Process Y is progressing around here, right? It's going up, 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 up. If it hits this point before X has, that is before there's anything in the buffer, process Y has to wait to receive the data. It is only after process X has passed that process Y can continue. What does this mean? That means that possible states of the execution are here before the synchronization, here after the synchronization, or here where X is past the point where it filled the buffer, but Y hasn't gotten these yet, there yet. These states are completely blocked by the synchronization. This would require Y to advance past this point when X hasn't done it, and that's blocked by the synchronization code. The net effect of all this is it reduces the phase space, and the phase space tells us, or is directly proportional to the entropy or the order of the process. With this synchronization here, the phase space is reduced to these three regions, but this region is completely inaccessible. We only have 75% of the original space, and that means we can only have 75% of the entropy, because the entropy is the order of states essentially, and the maximal entropy is the states can be spread out anywhere, but here they aren't. Here you can't have them, so you have less order, less entropy, and it turns out that that requires work. I'm going to skip ahead to some of this. There's a standard relation between entropy and phase space. You can get it in in any thermodynamics or statistical mechanics book. But we can also get the entropy from combinatorics. In particular, notice that our state is essentially an ordered list of numbers. Okay, how many possible combinations give us the same population in that list? If every block is different and we've got n processes, then you've got n different numbers, and those could be combined n factorial different ways. If everybody is in the same state as in a barrier, you've got all the processes in the same block. There's only one possibility, and there's only one combination. Now the entropy, the Boltzmann entropy, is just the logarithm of all this. So the logarithm of n factorial is going to be a pretty large number. The logarithm of 1 is going to be 0. So there's a big entropy difference implied by the same thing. So what we can do, we can predict the entropy. We can say, okay, we got this synchronization. This synchronization involves these particular restrictions which cause the phase space to be reduced by some fraction f. So we calculate what the full space phase would be. That's just, hey, all bets are off, all combinations are possible. We multiply that by the phase space, by the fraction of the space phase that is allowed, and then we take the logarithm of that, and that allows us to predict what the entropy of the execution with synchronization is going to be. And then we built a thermal model of this. This gets better. We can now say, okay, we can now get an analog for temperature, which is like how spread out are the states. You know, you've got everything in the same state would be absolute zero, right? Everything is perfectly ordered, but higher values of temperature would correspond to more spread between processes, and greater spread between different processes would mean higher temperature. Now, once we got an entropy and a temperature, we can use this equation of state borrowed from thermodynamics and say, hey, why don't we predict how much work is required to reduce the entropy like we know it's going to be reduced by this synchronization? So we did that, and then we realized, okay, we need this amount of work that corresponds to this change in entropy and temperature, because you need both. Okay, once we got that, we can say, okay, we need this amount of work. Where's that work coming from? The power input to our execution is just the cycles that are being driven into the CPU, right? So that's the rate of work that's coming in. Now we know how much work we need to synchronize. We say, okay, instead of advancing the computation, the work that we do to synchronize has to come from the clock same way, and the fraction that we need to synchronize represents slowdown of the computation. So we measured, and we can predict. For instance, this was the same code that I showed you the graph before. It's something called a downhill simplex optimization, in which you kind of iterate, and by searching around, you start from a random point, you search what the function looks like near there, and then you pick the direction that looks like it's heading downward, in whatever that means in 17 or 48 dimensions. You pick a direction that's going to lower values, and then recalculate there, and so on. And by kind of wandering around more or less randomly, you do tend to head downward until you hit a minimum, and then you stop. It's one of the standard synchronization techniques.
You have 5 more minutes, Professor.
Okay. So, well, what I want to show you is this. The time predictions are, we compared the difference in times between synchronized and unsynchronized with the predicted differences in time between synchronized and unsynchronized. And it's pretty close, see? We predict 0.4, we get 0.45. We predict 0.41, we get 0.37. This one's the only one that's off, really, and it isn't too far off. We predict 0.42 and we get 1.26. We tried this with a different program, a program that doesn't quite match our thermal model as well, but our predictions are still good. We predict, in this case, a difference between synchronized and unsynchronized by a factor of 4.7. Or rather, we observe 4.7, we predict 4.57. As we increase the number of processes, things get worse until right here with 48 processes, the synchronized execution was 18 times slower than the unsynchronized execution, and we predicted 19 times slower. You don't need to go into the details, but what this means, though, is that we really can't ignore the synchronization costs. It's kind of perceived wisdom in parallel computing that for bigger and bigger problems, you can ignore the data transmission cost, which is true, because say these executions are taking on the order of 10 seconds, but transmitting data from one process to another takes something like 20 milliseconds. So you can ignore that. What you can't ignore are the synchronization weights. And that's what we're measuring here. These entire predictions are not done by any model of what the communications look like, what we do to synchronize. It's just dependent on what happens to the phase space. So it depends just on entropy reduction and nothing else. So that means we can't get rid of it. It's not like we can use better methods. We've got a factor of 18 slowdown here. And it's not like we can synchronize using a better method. We can do it in hardware. It's not going to work because whatever we do, it's still going to need to reduce the entropy, and that takes work. There's no getting out of it. So the question is, how do you do it? How can you do this without synchronizing? And this is the point. We can't get real determinism without synchronization. We can't get causality. We can't preserve causality without, well, can we preserve causality without synchronization? And the answer is maybe. The universe, for instance, doesn't synchronize and it preserves causality, and there are speed of light delays from everywhere to everywhere. The thing is, if we know how old data is, then maybe we can do something deterministic with it, right? We might not need to actually reduce the entropy as long as we know that the data we're getting, we have some kind of way to compare when that data was generated to where we are now in execution. So that's the trick. Now, we rejected all the standard methods because they're not enough. Timestamps. Timestamps are conventional. You put a timestamp on the data that you're sending or receiving from some other process, and you know when that was generated. But a timestamp doesn't tell you anything about the execution, because different processes executing on separate hardware are going to advance at different rates. So just because something's been there for been advancing for 5 seconds doesn't mean that it's at the same position in the code as some other process that's been advancing for 5 seconds. Step number doesn't cut it either, because as we see from way back here in the control flow graph, suppose, for instance, you're at block 11. There's multiple paths you can take to block 11. If you're at block 20, same deal. There's multiple paths you can take there that involve different step numbers. So step number is not a direct comparison because of multiple paths. You might say block number. Okay, block number at least tells us we're doing the same code. If we were on block, for instance, we're on block 10, we clearly are always doing the same code. But now, what iteration of the same code are we doing? How many times have we gone through this one? There's multiple ways of getting to block 10. So just because we're in the same block doesn't mean we can trust the data. If we synchronize, for instance, we put a barrier at 10, then on every iteration of the loop, we're going to synchronize here, and we at least know that whatever we're doing corresponds to the latest iteration of the loop. But we don't have that without the synchronization. So what is the answer? Well, the answer is we synchronize, and we indulge in large delays that are of the same order of magnitude as the total execution time, or we try to derive approximate causality by doing things that are approximate combinations. How do you do this? Well, you analyze the control flow graph and you can see, you can identify, the trick is for every point where execution can diverge, like here, we call this thing a split. There's going to be a matching merge point where it joins together. So we know, for instance, that this point is a merge for here. Here the execution splits up. Here it merges again. We can use that to, and these split merge pairs are always nested. We can use that to derive a nesting level that tells us how deep are we into a code block? How deep are we in choices? Are we in a region that everybody's doing the same? So for instance, here we go up to a nesting level of say 2. When we get back here, we're back down to a nesting level of 1 or 0. If we get a combination of step number and nesting level, we can get some idea of where the execution is. What it amounts to is we create a time vector. Every time we got a split, we increment the nesting level and we track steps just at the new nesting level. So we have a time vector that says how far did we get in in nesting level 0, how far did we get in nesting level 1, and so on. And by having these separate times, by looking at that vector, we can see if we're at the same vector, then step numbers probably match. If we're at different levels, nesting levels, then we look down at where were we when that other process was at that level. And that way we can get some comparison for at least what is the ordering of these various values. And that at least should tell us, I mean, it won't replace a hard synchronization if we need determinism, but at least it tells us how good is this data? Is it data from our far past, in which case we can ignore it, or is this other process at a stage close to where we are so we can use it? Anyway, there's obviously a lot of extra work done here. A lot of it has been done previously on different lines of research, like this whole identification of splits and merges and nest levels is something that I did 20 years ago to analyze how task parallel groups could form during a parallel execution. So I can just leverage all of that for this. But the idea, the concept and the idea is, let's try to find out as much as we can in a relatively inexpensive way about what was the execution state of other processes when they generated the data that we want to use. And that gives us a measure of how trustworthy that data is. And that's as far as I got. This probably is the start of maybe another year of theoretical work and new experiments. So thanks. And is there time for anybody to ask a question? Or if not, you can all email me.
I have a question.
Yeah.
So would tracking the synchronization rates be easier if you were using like quantum computing or a faster computer, or would it sort of plateau out?
It would probably plateau out. The deal is, these are the predictions here are comparative predictions. This is what this is saying. For instance, when I'm saying the synchronization is costing you a factor of 8, that means the work you do to synchronize is 8 times bigger than the work that was required to just do the computation in the first place. So that just means you do it faster. Okay, maybe synchronization costs you 8 seconds in this case, and maybe if you were doing a quantum computer, doing it on a quantum computer, it would be 8 picoseconds. But that means that the original computation without the synchronization would have taken 1 picosecond. This is a proportional factor. It's the cost is derived from the phase space, and it gives you, relative to the energy available, how much do you need to synchronize. So it would scale up or down with the size of the problem and the speed of the computer, but the proportion would be the same.
Thank you.
This is the other trick, by the way. It is conventional that you can ignore communications cost as your computation cost increases for parallel problems, but the synchronization weights arise from differences in execution rates of different processes. So basically the entropy is the same regardless of what the size of your problem is. So your synchronization costs are, your synchronization weight costs are not going to go away for bigger problems. So you need to do something else if you want to be able to finesse that somehow. Okay.
Are there any additional questions?
Yeah. And I can have a kind of a final comment. The laws of thermodynamics are inescapable, evidently in any possible universe, because they depend on the mathematics of combinatorics, which is presumably the same. So even if the laws of physics were different, you would still have issues with entropy. It's, you can't win, basically, is what this is saying. Anyway.
Thank you so
Wow.
much, Professor.
Very happy to be able to to talk about this. And hey, expect the paper in about a year, going into total full detail on this. So thanks for inviting me. Bye.
Bye.
Thank you, Dr. Gomez.
Okay.
I mean, I remember when I came here for interview, I met Dr. Gomez, and we always had this discussion between quantum computing, classical computing. He brings computer science and physics. That's all those dimensions. It took you a while to put all those links together when you talk to him. So you have to be really, really fully focused.
Hey,
so you need to link all of that.
This represents the kind of the merging of what I thought were 4 different research lines that I'd been following through over 20 years. So I'm very happy about this. I'm really enthusiastic with it.
It's amazing. Thank you so much for what you are doing.
Okay. Anyway, I'm going to stick around and listen to you.
Okay. Well, I can start. I will. In my presentation, I will use a style of bring you back where I started, where we are right now, and where I'm heading towards. So maybe some of my students, because they had my classes, they saw some of my presentation or partially, but I will share also more what we did over the summer and where we are heading moving forward with the topic of aging in place. So if we are going to start, I can share my screen and we go from there.
Yes, go ahead.
Okay. Soon you can see my screen.
Yes.
All right, perfect. Let me just. All right, well, welcome everyone, and thank you so much for having me and inviting me to this wonderful seminar. I'll be talking about aging in place, a multi-sensor data fusion approach. As I said, I'll take you back from where I started from my PhD a couple of years ago, like 4 years ago, and then continue and see where we are and what the pandemic, made to us, so we can stop, or we stopped some of this research. Hopefully, we can resume when things be back and face to face. So talk about the motivation, design methodologies, findings, conclusion, and where I'm heading in this research. I'll make it a little bit fast. I know we have almost 30 minutes left for this seminar. So what's the problem that I start looking at is the older adults. All of us eventually will be older adults. The number of seniors are increasing, and we need to provide like more of an assistive care. The problem with that is cost. For example, Alzheimer's disease costs like 18,000 to 36 per individual. I believe this is yearly, could be. Nursing home care costs 70,000 to 80,000 annually. So not only this cost, we have another thing of the caregiver gap, and we noticed that when we have this pandemic, we were like dying to have, a care provider to join and help and fight this pandemic. So definitely there is a short and understaffed nursing homes. Another factors is the 80% of the over 60 are living with at least one chronic disease. 89% of seniors prefer to live independently and to age in a place. And that's kind of the key word here is aging in a place. That's kind of the motivation. Definitely being part of a nursing home or being under the care of family, a member, it's good. But if you want to age in a place, you have your memories, you have your the place where you are more comfortable with. So for example, the center of CDC, they define aging in a place as the ability to live in one's own home and community safely, independently, and comfortably, regardless of age, income, or ability level. So that's kind of the challenge. And people hate to leave their homes and go somewhere else. So they want to do that. So this is kind of the motivation. Yes, I want to age in my place, but it's not easy for me to live independently. Age-related issues, physical limitations, perceptual limitations, cognitive limitations, chronic age-related disease like dementia or Alzheimer. It's huge research there. Fun and trying to figure out solutions either in technical technology side or in biology side or medical side or medicine. But definitely we can use technology to help and support and provide more assisted living for people who are under this category. Another motivation was the fall, which is kind of a scary thing and most concern for elderly. I mean, I might be staying at home, I might have issues mentally or cognitive issues, but falling is a problem. With this age, the consequences of the fall can be huge. And so early detection of the falls, or not early detection of falls, basically early assessment of the person can be and the risk of falling will be very important so that we can prevent the fall. So one option or the first work is, can we identify this is a fall or not a fall? If I'm living alone and something happened, how can I tell this is a fall or not? The other option is, can I reduce the risk of falling? That means what we can do in order to do that, what kind of system we need to install, or what signals or measures we can get in order to anticipate or predict that there could be a fall. Also, people hate to be under camera, like I'm in my home and the camera in front of me, just under surveillance. Definitely privacy is a concern for these people. Integrating the new technologies in order to help and develop solutions and fully integrated solutions is very important. But as I said, there are different challenges here. Detect a fall, predict a fall, and protect the privacy of the elderly or the person generally. So the question here is, can we have an intelligent assistive living system that allow elderly to age in place? That's kind of the question that I started when I was in my PhD, continued while I'm still in my research, and hopefully keep continuing that when we come back, on campus. As I said, in order to provide such system, we need to have a system or systems to be able to detect falls, measure the functional decline. Like Freddy is doing fine. In a month from now, we notice that he is limping. There is something wrong with his walk or the stride, his walk stride or gait estimation. What's going on? That means something is not right. So let's just keep an eye on that. Detect the presence of multiple people, and that's very important to have like a social factor or social effect here. If there are multiple people visiting me at home, or let's just say kind of grandma, grandpa, visiting them, or my parents. My dad is like in his like mid-70s now, so I can relate to him as an elderly. So I want to make sure, is he alone or he has somebody else? So it was good to identify or have the system also recognize that there are other people there, and we need to find our target person. Who is that target person that we are most interested in getting the data from? Profiles different personnel from the scavenge signal. Now, this signal, as I said, we have different sensors. The sensor that I worked with was a floor-based sensor. Other people use their smartphones because they have, like, the capability of getting some of physical or location. Other people use Kinect for imaging. Other people use mics. They can install an array of mics in the living room. So if a fall happened, we can get, analyze the sound profile and say there is a normal noise, or it's an actual, an acceptable signal, or it is an actual fall, or something happened. So the type of the signal that we scavenge, we'll get the data from. Also, we can get maybe more information out of it. There are different techniques we can look at. So it's not just about solving a problem by having one solution. And maybe I'm trying to rush to the conclusion now. It's not enough to say it's one solution will fit all needs. Again, as I said, different people work in different systems. In my case, I worked in a floor-based sensor. Floor-based sensor handles the issue of privacy. Let me stop that. It handles the issue of privacy. It's a completely, as you can see here in the video, it's a system installed under the carpet. You walk, it's activated. You don't walk, there's no activation. No cameras involved. Even though you can see some cameras here, this is for my analysis, for ground truth analysis, because I want to make sure that whatever decision I'm trying to make here, decide is this a fall or not a fall, is based on a ground truth, some other kind of a system validating my work. So yes, I solved a privacy issues, but is my system 100% accurate? That's exactly what we are doing here. So I'll show you a video, or before I show you the video, I'll tell you exactly what is the system is all about. We have a sensor. You can call it pressure sensor, capacitive sensor, charging, discharging sensor. That sensor is going to generate an analog signal. This analog signal gets amplified, ATD conversion, so that your computer microcontroller can understand it. The microprocessor, you can run certain algorithm to do some thresholding. From there, you generate your data. The way I use my data here, the first level of work is translate this analog value into digital value. So I ended up with, well, I have 128 sensors. I ended up with an image, kind of, or a matrix of 128 binary value, 0 or 1. From there, I was able to apply different algorithms to say this was a fall or not a fall. Is this a normal walk? There's no walk, and something like that. So this kind of, in brief, what our system is all about. You can remove my system here, or this floor-based system. You put maybe a Kinect, where you take like depth images. You can bring it in here and do image processing, then eventually get your results. So that's why we can change the system. Eventually, the techniques you are using, computational intelligence, artificial intelligence, machine learning, whatever technique you are using, depending on your data. Is it an image? Is it a real-time series data? Whatever type of data it is. So once I get my data, I run my algorithm. Either I have the option to keep my data locally in my, I use Raspberry Pi, Jetson NVIDIA, forget the name, TK1. Yes, it was the first generation of NVIDIA, Jetson NVIDIAs. So I use that one, so I can keep it there. Or if I have really huge data, as Dr. Gomez mentioned, you might have a huge data there. Maybe whatever your Raspberry Pi or Arduino unable to handle this, so you can send your data to the cloud, where there you can do like more sophisticated analysis and algorithms. Once you have your data, you can store it. You can build like dashboards. You can do analysis, make decision, and all of that. Add alert system. So that's kind of the big picture of where we are, where I was, and where I'm going. So if you look at this, I show you like a video here. There's one of my colleagues in the lab walk in the carpet, under the carpet with 128 sensors. So we are doing like different setups. walk, fall. So he's walking now, as you can see. You can see the sensors are active in yellow. He's walking, stop, no activity. Now he will fall. So you can see how this, like the number of yellow or activated sensors just increased. So we use this, all those, he performed 10 experiments. I have another 10 people do the same thing. So we have like a lot of data. We use this data to build like data set, and use computational intelligence classifiers to say, is this a fall or not a fall with a certain accuracy. So that's typically kind of what we did. All those are stunt actor because it was difficult for me to bring an actual elderly to be in the lab and do all this, because that's gonna be, they will be like in bad shape in that situation. So as I said, the way we, sorry. Go on. All right, here we go. So this is kind of the frame by frame analysis to the count of number of active sensors, because if you're not steering on the sensor, it's not be active, will not be activated. And this is one of the issues in my system. So if you are standing still, you cannot tell who is there in the carpet, because completely discharged, there is no activity unless you move or fall or stand. So this is kind of was the motivation. This figure tells us, oh, wait a second. That means if I was able to find or apply a certain algorithm to detect the size of this activated sensors, that would be great. That can tell me either there is a fall, or there are maybe multiple people at the same time walking in the same area, or there could be a noise in my system, right? So part of my low kind of accuracy of my system, some of the sensors were dislocated or disconnected, so it created a noise in the carpet. So I have to fix that and rerun the algorithms. So we applied like sliding windows, or applied machine analysis. So the way we use it, I use connected component labeling algorithm. So when you look at your image, you can look at all those neighboring sensors with 0 and 1, because I use binary, so it could be 0 and 1. I didn't use like grayscale image, so we can have an actual value of the pixel. I used a binary one, which worked fine for the sake of what I'm doing. So using this connected component labeling helped me find the size of the largest component, because in the same carpet or the same sensor, the same matrix, you might find a huge component, or you might find a small component. This small components could be a noise because you move in the carpet. Some of the sensors get activated because of the charge-discharge thing. Maybe some humidity in the atmosphere. So we were doing like sorry about that. So we're doing kind of trial and error experimental result. Then we said this is the threshold that identify the person as a fall or not fall. So this is kind of some of our results. So we did the fall, we did fall detection, all looks good. Yes, there is a plus minus or certain accuracy, but we were able to say that person has fallen. Then we were able to alert the personnel in charge, or the healthcare provider, that something is happening here. There could be false alarm, and that's one of the problems of such systems. Then we said, okay, we detect the fall. Can we assess the risk of falling, right? That means, can I monitor my father's while he's living alone, going back and forth, for example, to the restroom or to the kitchen, or just during the day? Where will I be able to say, is he okay? Or there is a change in the gait, or there is a decline in his health. So we did what we call gait estimation. Same thing, we built the system, but at this time, it's difficult for us to analyze the gait by video cameras, so we can authenticate our work. I brought what we call a gait ride. This is a carpet that used in most of physical therapy clinics, so that they can measure your walking and the exact gait, and the stride length, the step length, the walking speed, all this information that is related to analyze, are you doing fine, or there's something wrong with your walk? So we use this experiment, the same thing, brought 10 people, do the experiments, do the work, we applied different algorithms. Then we said we are able to kind of get a really very comparative results. So now we are saying, okay, the system is working. I can use the same carpet system to do both fall detection or fall if there's a fall, and at the same time, if there's a decline, and assess if there is a fall or not. So based on the result, I say, okay, last week I was working this is my stride length, this is my walk speed. Now, 2 weeks from last week, there's a decline. That means something wrong. So I can relate that to be there is a risk of falling. Keep going. I'm done with that. Again, I'm going fast. I'm not going to go into the details because I want to show a lot more what we did in the summer. Counting multiple people, same thing. What's happened if there are more than one person there? Can I detect something going wrong in my parents' house? Or if they have visitors there? So within the same area, we installed the carpet. We had multiple people walking in the carpet. In that experiment, I brought my family, my wife, my 2 kids, to help me with this experiment. So we were walking in this carpet in different directions, opposite direction, parallel directions, 4 at the same time, 2 at the same time. And we were, again, using connected component labeling algorithm to solve such problems. So we are able at every frame to count how many people are there. So we kept track of, of the path. So we were able to say, yes, look, at the beginning of the walk, I have 4 people walking in different directions. But at the end, we were able to say there are 4 people. But the problem is in the middle. The moment we are close to each other, and the nature of that sensor, all of them get activated, the movement with the noise, you cannot tell. Yes, there are people there, but how many of them, we don't know. Now, who is our target person? We don't know. So this is another limitations of our work. Yes, it is working, but it's not as to be that much to identify our target person. So then we said, okay, wait a second. We are done with all of that. Can I get more information? Remember when I talked about the raw data that are provided by that sensor, this analog signal itself. Can I get more data out of it? Can I measure how much energy that signal has? What are different frequencies are provided? What are different features? Can tell if my father walked or if I walked in that sensor, can I get more or different walk kind of profile? If that was successful, that means here we go, perfect. And we can label it, this is Fadi's walk. Whoever walks in, we don't care because this is our audience. So we keep targeting that person. It was a good approach, a good experiment. Honestly, we get all those raw data, connect this directly. This is our sensor, by the way. It's a 2 layers of the foil for we cover the food with. So we create an isolator, so like a charging, discharging. The moment you step in it, build the charge, remove your foot, discharge. So that's kind of as simple as that. So we built an analog signal, sample it, and then we applied mel frequency, Capstral coefficient, another, to extract those features. We did, different algorithms. We were able to get some kind of close results, but honestly, they were not that much of a big deal. They were published, they were accepted. I believe we need to do more work in those algorithms or in the sensors to reduce the effect of the noise and the humidity around us. So looking at our system by itself, it was a success. Yes, it's a standalone system. It worked. There are some false alarms, but I was able to achieve more. But is single sensor enough? No, obviously it is not enough. If something happened and that sensor failed, complete noise, gonna send a continuous false alert. There are pets moving around. You throw the pillow somewhere else. How the system will respond to those things. False alerts. Walk identification. Yes, I need to identify the people. 4 people are walking, or I am myself walking. Can I identify as fast as possible? Some algorithms, when it comes to those, takes time. Can I do parallel processing to that? Can I have a high computing computer to run this? Is it within the scope or the budget that I can afford or not? So too many things that we need to think of. So the solution, or kind of the conclusion, is this is kind of bigger picture of the system. The conclusion is multi-sensor fusion. So it's not enough to depend on that single floor-based sensor. I should be depending on other sensors. Data fusion. If I'm depending on different sensors, that means each sensor is going to provide me with different data. How can I merge this data, fuse the data, and get the best of it and combine it and build a smart decision system out of that? Can I use standalone application or hardware, Raspberry Pi, Arduino, or a Jetson, NVIDIA small those microcontrollers? Can I say, no, there's some difficulty with that. Let me put a Wi-Fi compatibility to those, a data acquisition system and send the data to the cloud. Is the cloud the best option? Security issues, access time, latency, power, security. So there are different kind of features that are things that we need to worry about. So as we said, better to fuse multiple sensors. We have floor-based, we have vision or Kinect, PIR, passive infrared sensors, RFID, ultrasonic, pressure sensors, wearables, you name it, right? And that's kind of the moving forward. That's why I was hoping we will be back in face-to-face, because the way to do this, we have to be in a nursing home, installing our system there, floor-based, connects, and all of that, so we can collect data and see, yes, can we do that or not, to test the efficiency of our system. Feature extraction. As I said, each sensor data or sensor source provide different type of data. Time series data, image data, whatever you name it. So we need to better handle this data and extract features from them so that we can build a classifier. If you need to have some artificial intelligence or computational intelligence, definitely you need to have a data set to train your network so you can make a kind of a good prediction. Without this, it's difficult. So we need to go dig deeper to find what are the best features we can extract to build our data set to be able to do that. As I said, merging the data or fusing the data to make decision and provide a real-time decision. Because why real-time? It's not enough for me to just go and log into the server and get my data from there. No, it has to be real-time because it's people's life and the state. So this is what I've been doing, continue working on that till this pandemic hits and we stopped. In the summer, I have like 2 students, computer science students and computer engineering students who worked with me over the summer. And we used AWS as a kind of as an environment. Even though that's not my goal, to be honest with you. My goal is to build a framework, an open source framework, because I believe in open source and I believe that we need to support our community. To build a framework completely free to support multi-sensor data fusion, everything built from scratch with a modular level so that we can say, okay, this person has dementia. That means they cannot rely on wearables. So wearable is not an option. So we just figure out that build and customize solution for the person who we want to age in place. So what we did, we said, okay, we don't have an option. We don't have access to nursing place. Let's just build a simulated environment. So we used Amazon Web Services as our hosting environment, data analysis and data monitoring and decision making and alerting system. Internet of Things, obviously, because we are using features from AWS, and this is kind of the edging in space. That's why the long title, as they say. So what we did, as I said this scenario before. Grandma, my father lives alone. Did he take his medicine? No. How we can ensure that he or he did or didn't take medications? Or for example, is the AC on and off? How's the temperature inside the room? Are they within the normally operated? And you can name different things. Oh, he has issues with the light. Is the light intensity high, low? Can we control all of that? So too many things you can install, too many sensors you can install, more data you can gather. At the same time, you can build, aggregate this data, and from there, profile that person. You say, these are the thresholds. This is what works, what doesn't work. Here is the time where I need to trigger an alert saying, oh, there is a risk of dehydrated or something like that because the temperature is high. Either we automatically control it and lower it, or has somebody to be moved in and check that system failure or what's going on. So that's kind of the scenario. Again, this was done because of the pandemic. So we duplicated the system in 3 places. We used temperature sensor, humidity sensor, magnet sensor, PIR motion detection sensor, and heart rate sensor. So we thought this is kind of some sensors we can collect data from, analog sensors, digital sensors. motion detection. The magnet sensor, we put the magnet sensor on the medication drawer. So if there's the door doesn't open at 8 a.m. in the morning, that means my father didn't take his medication. So we send an alert or make some decision based on that. So this is kind of the system we built. We use Raspberry Pi and we integrate all those services together. We duplicate this system into 3 different locations, in my home and in other students' homes. We connect them using Amazon, and we install the AWS and all those Raspberry Pi. So we're able to communicate, sense data real time, and send control back to those to turn on, off, or alert the person as well. So that's kind of the hardware, that's the setup. We were hoping there will be in a nursing homes, and we'll have all the data collected from different nursing homes to a server located on our campus, and we can do the analysis. So again, I know we didn't have much time, but this is kind of the layout or the flow we followed. We built everything from scratch. We just rely on some services to do that communication on Amazon AWS. So we interface AWS with Raspberry Pi. We send the data to the stored database. We use like Amazon Elastic to benefit from data storage, analysis, classifications, decision making, alerting system using the Amazon SNS, what we call it simple notification services. So yes, we relied on Amazon in that sense, even though we wanted to build that ourselves as an open source framework for multi-sensor data fusion, customizable. And that's hopefully I'm inviting you guys, all CSE students, hopefully if we need to be part of this to start working on, maybe starting in the fall. Again, this is a quick video. I should be making this fast. So to show you, like, everything was done on those Raspberry Pi. We built our monitor, we send the data to the cloud, we make the alert based on a 13 threshold. We monitor the data real time. We were able to look at the temperature, the humidity, the door open or closed for the medication. Then we created a trigger. If that door was not open, that means there is a medication was not taken. Then we sent an alert here. I'll show you that towards the end. We sent an alert by email saying this person didn't take medication status. So I received that. Here we go. I need to take an action. Or they just ring a bell closer to the person or to the elderly to a reminder, hey, you need to take your medication. It was due at 8 a.m. and now it's the time. So this is what we have done. This is kind of some of the data we collected, and this is some notification systems. So yes, we were able to do this. We were able to aggregate the data, collect data from different sensors, aggregate the data, and build a decision support system. Where we are going forward, as I said, build an open source system with different sensors, different customizable systems. I would like to continue working on that. The thing that currently I'm interested in, and I would see if any of you guys will be interested, and all CSE students, is how to explore the impact of extended reality or the use of extended reality on the emotions of elderly aging in a place. Not in a place, sorry. So we can use Oculus because now they are wireless, by Facebook Oculus 2. Can I build a virtual room? I can call all my father's friends so they can, as if they are sitting in the same room, chatting, communicating, and in real and active. So mentally they are active, emotionally they are connected, and all of that. So this is a research I'm interested in. Hopefully over the phone, I got 3 of those, virtual reality hardware. And if any of you guys interested, like to be part of this research, I will invite you. Other than that, thank you for your time. I appreciate if you have any question, which I understand if you don't, because we don't have time, but I'm here to answer your questions.
Well, thank you, Professor. I suppose one question I have for students that want to get involved in your project, is there any sort of preferred skill level that you want people to have, like seniors only, master students? Could anybody interested at all get involved? Anybody interested can be involved. Because again, it will be, if you know more of, like Unity programming, definitely our virtual reality related experience or game development experience would be preferred, but definitely it's open for any computer science and engineering student. Thank you. This was an amazing project presentation, and your research is amazing. And it's exciting to see what will happen when back on campus.
Yeah, same here. Thank you so much for having us. And again, it was a really pleasure to be part of this, and also a pleasure to again hear and watch Dr. Gomez presenting, and it's an honor. Thank you.
Thank you both for your time.
I just wanted to tell you that I was really impressed by what you've done. You kind of answered as I was thinking, okay, but aren't there privacy concerns? You answered everything that I was thinking of as a question before I even got to ask it. So very good presentation. And I'm also looking forward to being on campus next year. I miss the interaction.
Thank you. Thank you. I appreciate it.
Yeah. So bye then, everybody.
Goodbye.
All right. Thank you. Bye-bye.
Thank you, guys.